So here's an elliptical orbit, a comet or something. Seems to be in the XY plane, so let's rotate it. So we've, all right. But now we have something interesting because here's R. The magnitude of R isn't constant. And here's the momentum. And as you know, it's speeding up when it gets closer. It's slowing down when it's farther away. So that's not constant either. The angle between them, well, that's changing too. But what do you think we might get if we actually work this whole thing out? First of all, what's the direction going to be? Yeah, it's going to be that way. And you think it'll be constant? Yeah, it might be. Let's see. So that's the angular momentum, and we'll tip it up. And it is being recalculated continually. And it looks like it actually is a constant, as long as that's the location we use to calculate the angular momentum around, and it's the obvious one. But suppose we actually did it over here. Whoa. So we don't have to choose the obvious place to draw R from. And so it seems like that center of the sun there, the center of the star, is kind of a special place. We could do it up here in 3D, but that's a pretty special location, and indeed the angular momentum around that location seems to be a constant. We've pretty much specified a vector when we're talking about angular momentum here, because we've got a magnitude and a direction, and that's a vector. These arrows are vectors. And there actually is a mathematical vector operation that we can use to go directly from those two vectors to the angular momentum as a vector. No right hands involved, which is a good thing, because that means we can actually write equations and make that work. And it's called the vector cross product. And how many of you have actually used vector cross products? Okay, maybe half of you. So we can write down that the angular momentum, what are the units of it, do you think? Yeah, so this one has units of meters. And the units of momentum are kilograms times meters per second. And sine theta doesn't have units, so it looks like it's going to be kilogram meters squared per second. Kind of an odd unit. And so we can write angular momentum about location A is equal to the vector cross product of R, which is that vector from A to the object, and P, which is the momentum of the object. And this is different from, remember we did dot products when we were talking about work. And dot product was a scalar. This is a way of combining vectors that gives you a vector as a result, so it's very different. And mathematically, what it works out to be, so you really can, so we can say direction right hand rule, but we could also write it like this. It's going to be a vector, And so what's the x component? Well, the x component of this vector is going to be, so let's write these vectors out. We'll just write r as x, y, z, and we'll write p as px, py, pz. And so the x component is equal to an interesting difference. It's y times pz minus z times py. So that's the x component. And the y component, well, that's z times px minus x times pz. And the z component, well, that's going to be x times py minus y times px. Now, how on earth do we remember all that? Well, one way to remember it is to realize that there's sort of a cyclic relationship. The x component involves y and z. The y component involves z and x. The z component involves x and y. So some people write it like this. So, and the way you interpret that is if you want the x component, then you start out with the y component of the first vector and the z component of the second vector, and then you subtract the z component. So x involves yz minus zy, y involves, or some people write this, xyz, xyz, and arrow that way, meaning if you want x, you take y and z. If you want y, zx. Okay, so there are various ways to remember this. There's also a way to do it with determinants, which you might know. Typically, the situations, this can get arbitrarily complicated. The situations we're going to consider are typically sort of easy. We'll tend to orient the plane of these two vectors with the plane of the screen or the page, so that gives us a fighting chance. And in general, here's what cross products look like. So here's a plane shown by this grid, and there are two vectors in this plane, a red vector and a blue vector. And the magenta vector that's perpendicular to the plane is the cross product of those two vectors. So the cross product of two vectors, if you can figure out what plane those two vectors lie in, then the cross product is either into or out of that plane. And let's see what happens. So I can move this vector around, I can stretch it, I can change the angle between these two things, and the resultant is changing. So let's be a little systematic here. So let's make so the magenta vector is the red vector cross the blue vector. And there's a right-hand rule for just this simple mathematical cross product too, and it goes like this. And it's worth learning. The order of these vectors matters. This is not commutative. So when we say first vector, we mean the one we wrote first. And when we say second vector, we say the one we wrote second. So we point our fingers in the direction of the first vector. That's the red one. And we have to have a stiff wrist to make this work. And then we want to bend our fingers toward the second vector through the smallest possible angle. And right now I can't do that without breaking my wrist. So I have to turn my hand over. So I curl my fingers from vector number 1 toward vector number 2, and I stick my thumb out, and it sticks out in the direction of the resultant. And so does it work this way? Yeah, because if I stick my fingers in the direction of red and curl towards blue, my thumb sticks in. And so what happens when they're collinear? Looks like 0. That's at sine theta, isn't it? What happens when they point the same direction? 0. So what's the maximum value the cross product going to end up being? They're 90 degrees, right? Or 90 degrees the other way. Or, and of course the length matters, so the bigger the magnitude of the vectors, the bigger the magnitude of the cross product. And the smaller the magnitude, right? So, okay, well, we'll actually practice this next time.